Right now, as you watch this, Earth is drifting through an enormous region of nearly empty space. Not empty in the way people imagine outer space to be empty. This is something different. The region surrounding our solar system contains far fewer atoms, far less dust, and far less gas than almost anywhere else in our galaxy. And this is not a coincidence. It is the aftermath of catastrophic stellar explosions that occurred millions of years ago. A chain of supernovae carved out a giant cavity in the Milky Way. And somehow, through the slow drift of galactic motion, our sun ended up almost exactly in the center of it. That cavity is known as the local bubble. It spans roughly 1,000 light years across. And understanding it might change how we think about everything from the formation of stars to the survival of life on Earth. To appreciate what the local bubble is, it helps to first understand what our galactic neighborhood is normally like. The Milky Way is not a uniform ocean of stars and gas. It is a complex, layered environment filled with molecular clouds, stellar nurseries, hot ionized plasma, and cool, neutral hydrogen. Between the stars, there is a diffuse medium, a soup of atoms, ions, dust grains, and magnetic fields. In some regions of the galaxy, this medium is incredibly dense and cold, the kind of environment where gravity can slowly pull matter together and ignite new stars. In other regions, supernovae and stellar winds have blasted the surrounding gas outward, leaving behind vast low-density cavities. These cavities are called superbubbles, and the local bubble is one of them. What makes the local bubble scientifically remarkable is not just its existence. Many such bubbles are scattered throughout the galaxy. What makes this one extraordinary is that our sun currently sits near its center, a position that turns out to be cosmically unusual, and which may have played a quiet but significant role in the history of life on our planet. Let us go back to the beginning of the story. Approximately 14 million years ago, a cluster of massive stars occupied a region of the Milky Way not far from where our sun would eventually pass. Massive stars burn fast and die violently. When they exhaust their nuclear fuel, they collapse and then explode as supernovae, releasing in a matter of seconds an amount of energy comparable to what our sun will emit over its entire 10 billion year lifetime. These explosions do not happen in isolation. When a cluster of massive stars forms, many of them will go supernova in relatively rapid succession over a span of millions of years. Each explosion sends a shockwave rippling outward through the surrounding interstellar medium. In the case of what became the local bubble, scientists believe that somewhere around 15 supernovae exploded over several million years. Each one added energy to the surrounding gas, heating it, ionizing it, and pushing it outward. The pressure from these successive blasts carved out a growing region of hot, low-density plasma. Think of it like blowing repeatedly into a soap bubble. Each breath inflates it further. Except in this case, the breath is an explosion of stellar proportions, and the medium being pushed aside is the interstellar gas of the Milky Way. The result was a cavity roughly 1,000 light-years in diameter, surrounded by a denser shell of compressed gas and dust. That shell, the wall of the local bubble, is where something especially interesting happens. When interstellar gas gets compressed into a dense shell, it creates exactly the conditions needed for new stars to form. Gravity can act more efficiently on dense material, and this is precisely what astronomers have observed. Along the surface of the local bubble, there are at least 7 active star-forming regions, dense molecular clouds, where new stars are currently being born. This discovery was not made through a single observation. It came together through years of painstaking data analysis, culminating in a landmark study published by researchers at the Harvard-Smithsonian Center for Astrophysics. The team used data from the European Space Agency's Gaia Space Observatory, a spacecraft that has been mapping the positions and motions of over 1 billion stars with extraordinary precision to reconstruct the particular three-dimensional structure of the bubble and the molecular clouds on its surface. What they found was striking. The star-forming regions that astronomers have studied for decades, places like the Ophiuchus cloud, the Perseus molecular cloud, the Taurus cloud, are not scattered randomly through space. They are all sitting on the surface of the local bubble, arranged like foam on the edge of a giant cosmic soap bubble. The bubble shaped these regions, It compressed the gas that will eventually become new stars. In a very real sense, the local bubble is a stellar nursery machine, a structure that simultaneously destroys old stars through supernovae and creates the conditions for new ones to form along its expanding wall. The lead researcher on this project, astronomer Alyssa Goodman of the Harvard-Smithsonian Center for Astrophysics, offered a vivid way to picture the galaxy's large-scale structure. She compared it to Swiss cheese. The Milky Way is not a smooth medium. It is riddled with holes punched out by supernova explosions, each hole lined with dense compressed gas, each hole potentially giving birth to new stars along its edges. The local bubble is one of those holes, and we are floating near its center. When this research was published, it confirmed something that astronomers had suspected for decades. Since the 1970s and 80s, scientists had noticed that the space immediately surrounding our solar system appeared strangely empty compared to the rest of the galaxy. The interstellar medium near the Sun had an unusually low density of neutral hydrogen, the most abundant atomic species in the cosmos. Something had cleared the neighborhood. The local bubble explained why. Now, here is where the story gets even more interesting, and where the question of our Sun's exact position within the bubble becomes significant. Our Sun did not form inside the local bubble. It did not cause the explosions that created it. 14 million years ago, when those supernovae were detonating and carving out the cavity, the Sun was roughly 1,000 light years away, in a completely different part of its orbit around the galactic center. The Sun takes about 200 million years to complete one full trip around the Milky Way's core. Astronomers sometimes call this duration a galactic year. Over the course of cosmic time, the Sun has completed many such orbits, drifting through different environments as it goes, sometimes threading through dense spiral arms rich with gas and dust, sometimes passing through relatively quieter interstellar regions. About 5 million years ago, a blink in galactic terms, but roughly the period during which our hominin ancestors were first appearing on Earth, the Sun drifted into the region occupied by the local bubble. As astrophysicist João Alves of the University of Vienna explained, when the research was published, the Sun wandered into this cavity as part of its natural orbital path around the galactic center, and it ended up very close to the geometric center of the bubble. Not perfectly centered, but remarkably close. This raises a natural question. Is it simply a coincidence that we find ourselves near the center of one of the Milky Way's large superbubbles? Or does the bubble's existence somehow relate to the conditions that allowed complex life to develop on Earth? The honest answer is that scientists do not yet know, but there are reasons to think the relationship may be more than accidental. Consider what life on Earth needs in order to survive and evolve. It needs, among many other things, a relatively stable environment. Massive disruptions, whether from asteroid impacts, gamma-ray bursts, or dramatic changes in the cosmic radiation environment, can threaten the complex biochemical systems that life depends on. One of the most persistent environmental threats over geological timescales is the galactic spiral arms. The Milky Way is a barred spiral galaxy. Its stars, gas, and dust are arranged in a rotating disk, and within that disk, regions of higher density trace out spiral arms that wind outward from the galactic center. The Sun is currently located between two of these arms, the Sagittarius arm toward the galactic center and the Perseus arm on the outer side. The Sun is about halfway between them in what astronomers call the local arm, or the Orion spur, a smaller secondary feature that connects the two major arms. When the Sun passes through a spiral arm, it enters a much denser region of the interstellar medium. The density of matter in spiral arms can be orders of magnitude higher than in the interarm regions. Higher densities mean more molecular clouds, more star formation, and critically, more massive stars, which means more supernovae. A period of intense nearby supernova activity could bombard the inner solar system with cosmic rays, dramatically increase the flux of high-energy particles reaching Earth, and potentially trigger significant changes to Earth's climate and atmosphere. Astrophysicist Miroslav Filipovic undertook a careful analysis of this idea using detailed models of the Milky Way's structure. His work compared the timing of the Sun's passages through galactic spiral arms against the geological and paleontological record of mass extinction events on Earth. What he found was a striking correlation. The 5 major mass extinctions in Earth's history, events that occurred approximately 415 million, 322 million, 300 million, 145 million, and 33 million years ago, appear to align with periods when the Sun would have been crossing or recently crossing spiral arm structures. This is not proof of a causal connection. Correlation in complex systems can arise for many reasons, and the uncertainties in both the galactic timing and the extinction dating are significant. But the pattern is suggestive enough that researchers are actively investigating it. If the Sun's passage through dense galactic regions genuinely triggers increased cosmic ray flux, and if that flux influences Earth's climate or ionospheric chemistry, then the trajectory of life on our planet may be partially written in the large-scale structure of the Milky Way itself. What we can say with greater confidence is that the Sun is currently in a relatively quiet cosmic location. Inside the local bubble, the density of the interstellar medium is extremely low. There are fewer molecular clouds, fewer massive star-forming regions nearby, and therefore fewer potential sources of nearby supernovae. The Sun has been in this protected harbor for several million years, and it will likely remain here for some time to come, since the bubble continues to expand, albeit now at a much slower rate than when the supernovae were freshly detonating. To understand how we know about the bubble's current state and its expansion, we have to look more carefully at the observational methods that revealed it. And that means starting with a different kind of bubble entirely. One much, much smaller, and one that the Sun itself creates. Every second, the Sun ejects an enormous stream of charged particles, primarily protons and electrons, outward in all directions. This stream is called the solar wind. It moves at several hundred kilometers per second and carries the Sun's magnetic field with it, sculpting a vast magnetized region around the solar system. This region is called the Heliosphere, and it extends far beyond the outermost planets. The Heliosphere is, in a literal sense, a bubble of solar plasma carved out of the surrounding interstellar medium by the constant pressure of the Sun's outflowing wind. The heliosphere has a boundary. At some point, the pressure of the solar wind diminishes to the point where it can no longer push back against the incoming pressure of the interstellar medium. This boundary is called the heliopause, and it marks the edge of the solar system in the most physically meaningful sense. Beyond the heliopause, the Sun's magnetic field no longer dominates the environment. Interstellar space begins. 2 spacecraft have actually crossed this boundary. Voyager 1 and Voyager 2, launched in 1977, within weeks of each other, spent decades traveling outward through the solar system and beyond. Voyager 2 crossed the heliopause in 2018, at a distance of about 119.7 astronomical units from the Sun. That is roughly 17.9 billion kilometers. Voyager 1 crossed it earlier, in 2012. The measurements taken by these 2 probes as they crossed the heliopause confirmed something theoretically expected but observationally challenging to verify. The density of particles changes dramatically at the boundary. Inside the heliosphere, the solar wind maintains a relatively low density that decreases steadily with distance from the Sun. At the heliopause, the outward flow of solar wind drops to essentially zero. And just outside the heliopause, the Voyager instruments detected a significantly higher density of plasma, roughly 0.037 particles per cubic centimeter, close to what models had predicted for the local interstellar medium. But then something curious happened. As Voyager 2 moved further from the heliopause, to a distance of about 124.2 astronomical units from the Sun, the density jumped again. This time to approximately 0.12 particles per cubic centimeter. That is more than 3 times what was measured just outside the heliopause. This density increase is not a mystery to scientists. It reflects the physical process occurring at the boundary between the 2 very different plasma environments. The solar wind and the local interstellar medium are both magnetized plasmas moving in different directions and at different speeds. When they meet at the heliopause, they do not simply pass through each other cleanly. They interact. The solar wind slows down as it approaches the boundary, and a region of compressed, turbulent plasma builds up just outside the heliopause, sometimes called the outer heliosheath. Think of it as a traffic jam in space particles from the interstellar medium piling up where the two flows collide, increasing the local density dramatically. This compressed boundary region is not just a curiosity. It serves a critically important function for life on Earth. The buildup of plasma at the edge of the heliosphere creates a physical barrier that deflects a significant fraction of galactic cosmic rays, high-energy charged particles accelerated by supernovae and other energetic phenomena throughout the galaxy. Without the heliosphere and its compressed boundary, far more of these cosmic rays would penetrate into the inner solar system and reach Earth's surface. The heliosphere is, in essence, a shield, and it is the first of the two bubble structures that protect us. The second and larger one is the local bubble itself, which removes from our galactic neighborhood much of the material that could otherwise produce cosmic rays close to home. The physics of the local bubble's formation and evolution are now relatively well understood, thanks to a combination of theoretical models and observational data. At its heart, the bubble formed and expanded as a result of successive supernova explosions. Each explosion released kinetic energy of roughly 10 to the power of 44 joules, or, written out as a spoken number, that is roughly 100 septillion joules. For context, our sun will emit its total lifetime energy output over the course of 10 billion years, and even that pales in comparison to the energy released in a single supernova explosion. Those 15 or so supernovae that created the local bubble did not all go off at once. They were spread over millions of years, one after another within the same stellar cluster. Each explosion reheated and re-energized the bubble, preventing it from collapsing back inward and driving continued expansion. When the bubble first began growing, astrophysicists calculate it was expanding at around 60 miles per second, that is roughly 100 kilometers per second. Over time, as the energy dissipated and the expansion decelerated, the outward velocity slowed considerably. Today, the local bubble is still expanding, but at a much more leisurely pace. Current estimates based on the motions of molecular clouds on its surface put the expansion speed at roughly 4 miles per second, about 6 to 7 kilometers per second. At this rate, the bubble will continue to grow for millions of years before it eventually stalls and possibly merges with neighboring structures. The Gaia Space Observatory was crucial to pinning down these numbers. Gaia was designed to measure the positions, proper motions, and radial velocities of stars with unprecedented precision. By tracking the three-dimensional motions of young stars and the molecular clouds they formed in, the Harvard-Smithsonian team was able to reconstruct not just the current shape of the bubble, but also the history of its expansion, essentially playing back cosmic time to determine how fast the bubble was moving at various points in the past, and using those speeds to infer when and how it formed. The three-dimensional reconstruction produced by the team is something genuinely new in astronomy. For the first time, scientists could see the local bubble not as a vague, poorly defined region of low density, but as a coherent structure with measurable dimensions, a surface populated by star-forming clouds, and a history that stretches back 14 million years. This has opened up a new way of thinking about how stars form in the Milky Way. The traditional picture of star formation focuses on the internal properties of molecular clouds, how cold they are, how dense they are, whether magnetic fields are strong enough to resist gravitational collapse. All of those factors matter. But the local bubble research suggests that the large-scale structure of the galaxy, the pattern of supernova explosions, carving out bubbles and compressing shells of gas, plays a fundamental role in determining where, when star formation happens. This is not a new idea in principle. Astronomers have long suspected that supernova-driven turbulence and shock waves can trigger star formation in nearby clouds. But the local bubble gives us a concrete, mapped, three-dimensional example to study in detail. Every star-forming region on the bubble's surface is a potential test case for models of triggered star formation. Every cloud can be traced back to a specific piece of the bubble's wall and its history of compression. The science of how stars are born just became a lot more observationally tractable. What does the interior of the bubble actually look like? If you could travel to any point within the local bubble and look around, you would see remarkably little. The interior is filled with hot, tenuous plasma gas at temperatures of around 1 million degrees Celsius that is so diffuse it is essentially transparent. The density is on the order of a few hundredths of an atom per cubic centimeter. By comparison, the air you are breathing right now contains roughly 25 times 10 to the power of 18 molecules per cubic centimeter. That is 25 quintillion molecules in a space the size of a marble. The local bubble's interior contains perhaps a few atoms in that same volume. It is as close to a perfect vacuum as nature produces at this scale. Yet this near vacuum is not truly empty. It glows faintly in X-ray light, a signature of the hot plasma that fills it. This soft X-ray emission was first detected by early satellite observations in the 1970s, and it was one of the original clues that suggested something unusual about our local interstellar environment. The hot gas was there, but the neutral hydrogen that should also be present was strangely absent because the supernovae had blown it all outward to the bubble's walls. Within this hot, empty interior, the sun moves. It orbits the galactic center, drifting slowly through the bubble, currently near its geometric middle but not permanently fixed there. Over the coming millions of years, as the sun continues its galactic orbit, it will eventually drift out of the local bubble and into whatever interstellar environment lies beyond. That environment may be very different, denser, more turbulent, or perhaps part of another superbubble formed by a different cluster of massive stars. There are good reasons to think that the galaxy is riddled with structures like the local bubble. Massive stars tend to form in clusters, and cluster formation is not randomly distributed through the galaxy. It concentrates in spiral arms, and in regions where gas clouds have been compressed by previous disturbances. Each cluster of massive stars that forms will eventually produce multiple supernovae, carving out its own superbubble. The Milky Way may contain dozens or even hundreds of such structures at any given time, each at a different stage of evolution, each shaped by a different sequence of stellar deaths. This picture of a galaxy filled with expanding superbubbles has implications for how we understand the cycling of matter through the interstellar medium. Stars form from gas. When they die, whether quietly as white dwarfs or violently as supernovae, they return material to the interstellar medium. Supernovae in particular return enriched material atoms heavier than hydrogen and helium that were synthesized inside the star during its lifetime and during the explosion itself. These heavy elements, carbon, oxygen, iron, silicon, are the raw materials of planets and of biochemistry. When a supernova explodes and pushes material outward into a growing bubble wall, it is not just moving gas around. It is distributing heavy elements through the interstellar medium, enriching the clouds that will eventually form the next generation of stars and planets. Life on Earth is made of atoms forged in stars that died billions of years ago, and the local bubble is part of the ongoing process by which those atoms are recycled through the cosmos. There is another intriguing piece of evidence connecting our sun's passage through the local bubble with the geological record of Earth. When cosmic rays particles accelerated to near light speed by supernovae and other energetic events strike interstellar material, they can produce radioactive isotopes that are not naturally abundant in the solar system. One of these is iron-60, a radioactive isotope of iron with a half-life of about 2.6 million years. Iron-60 is not produced in significant quantities by the sun or by normal solar system processes. Its presence in a geological deposit is therefore a marker of supernova activity in the vicinity of the solar system at the time the deposit formed. And iron-60 has been found in oceanic crust samples from Earth, in deposits that date to between roughly 1.7 and 3.2 million years ago, and also in deeper, older layers corresponding to activity around 6 to 9 million years ago. These deposits align with the expected timeline of supernovae occurring at or near the edge of the local bubble as the sun drifted through the region. The signal in Earth's crust is, in a sense, a fossil record of the same explosions that shape the bubble we now inhabit. The detection of iron-60 in Earth's crust has generated considerable scientific interest because it opens a direct geological window onto cosmic events that occurred millions of years ago. Multiple research groups have confirmed the signal in different sample collections from ocean floors around the world, making it increasingly difficult to attribute to contamination or instrument artifacts. The pattern of the signal with distinct peaks at different time periods suggests that the depositions were not continuous but came in bursts, consistent with the idea of discrete nearby supernova events rather than a smooth background. Some researchers have even proposed that a close supernova one occurring within a few hundred light-years of Earth could have briefly elevated cosmic ray flux enough to influence Earth's climate. Cosmic rays can ionize upper atmosphere particles, which in turn can affect cloud formation, and cloud cover influences surface temperatures. The mechanisms are complex and involve multiple steps of atmospheric physics, and the scientific community has not reached consensus on whether nearby supernovae actually triggered any specific climate events. But the possibility is taken seriously enough that it continues to be actively modeled and tested. What we can say with increasing confidence is that our location within the local bubble correlates with the Sun being in an unusually quiescent patch of the galaxy. There are no known nearby massive star-forming regions inside the bubble. There are no dense molecular clouds immediately threatening the solar system with elevated radiation. The nearest star-forming regions are all on the surface of the bubble places, like the Ophiuchus complex about 400 light-years away, or the Taurus clouds at similar distances, and they are producing stars of predominantly lower mass, less likely to end their lives as supernovae in the near term. The Sun will not encounter another spiral arm for tens of millions of years at the earliest. The bubble continues to expand, though at a decreasing rate, and its interior remains a relatively protected space. By cosmic standards, we are in a quiet period. The geological record of mass extinctions from spiral arm crossings is, for now, history rather than forecast. But there are open questions, many of them. One concerns the exact origin of the supernovae that created the local bubble. Scientists believe they came from a now dissolved stellar cluster, a group of massive stars that formed together, lived out their brief lives, and left behind a collection of neutron stars and black holes. The Scorpius-Centaurus Association, a loose grouping of hot, young, massive stars, is thought to be the descendant cluster, the younger siblings of the stars that exploded. It is located partly on and near the surface of the local bubble, consistent with the idea that the explosions creating the bubble came from this general region. The Scorpius-Centaurus Association is the nearest region of recent massive star formation to our solar system, and it has itself produced several supernovae within the past few million years. Some of the iron 60 found in Earth's crust may be attributed to these more recent events. Another open question is how the local bubble interacts with its neighbors. Space is not simply a collection of isolated superbubbles floating freely. The bubbles can merge, overlap, and exchange material across their boundaries. There is evidence that the local bubble is connected to other low-density regions of the interstellar medium, and that these connections create larger-scale structures called chimneys or tunnels through which hot gas can flow out of the galactic disk entirely. Astronomers are currently working to map these connections in 3 dimensions, using data from Gaia and from X-ray observatories that can trace the distribution of hot plasma. The goal is to build a comprehensive picture of the galaxy's bubble structure, what Goodman and her collaborators have described as understanding the Milky Way's interstellar medium the way we might understand the structure of a forest, not just individual trees, but the overall ecosystem and how its components interact. A third area of ongoing investigation is the surface of the local bubble itself. The 7 star-forming regions identified in the initial research represent only the most clearly mapped portions of the bubble's shell. There are likely additional clouds and filaments associated with the bubble's boundary that have not yet been fully cataloged or connected to the larger structure. As Gaia continues to release data and as new telescopes come online, particularly in the infrared, where cool molecular gas can be detected, even through dust obscuration, the picture of the bubble surface will become more complete. One such telescope is the James Webb Space Telescope, which, though primarily designed for cosmological observations and the study of distant galaxies, also has tremendous capability for studying the interstellar medium and star formation in detail. Its infrared sensitivity can probe the internal structure of molecular clouds that are invisible to optical telescopes. Combined with Gaia's astrometric data, the 2 instruments together should allow researchers to study the star-forming clouds on the local bubble's surface with unprecedented resolution. There is also a practical dimension to all of this that is rarely discussed but is genuinely relevant. As humanity begins to think seriously about interstellar travel, not in the near future, but as a long-term aspiration, the structure of the interstellar medium matters enormously. A spacecraft traveling to a nearby star, even at a fraction of the speed of light, would spend years moving through interstellar space. At even a tenth of the speed of light, a dust grain of about 1 microgram would carry the kinetic energy of a small explosive. Spacecraft traveling at high speeds through dense interstellar medium full of dust, grains, and gas would face serious physical risks. Inside the local bubble, the interstellar medium is nearly empty. Dust and gas densities are a fraction of the galactic average. If humanity ever develops the technology for high-speed interstellar travel, the local bubble represents a relatively benign corridor through which nearby stars could be approached. The nearest star system to our Sun, Alpha Centauri, at a distance of approximately 4.2 light-years, is well within the bubble. Tau Ceti, a star at about 12 light-years distance that has attracted attention as a potential host of rocky planets, is also within or near the bubble. These destinations, among the first that would be considered for any interstellar mission, are accessible through the local bubble's comparatively cleared space. This is not to suggest that interstellar travel is imminent or easy. The challenges are immense and extend far beyond the density of the interstellar medium. But it is a poetically satisfying observation that the same cosmic accident, which may have contributed to the stability of Earth's biosphere, the Sun's presence in a vast, low-density bubble, also happens to offer a relatively clear path toward the stars. The local bubble, ultimately, is a story about how connected everything is in the cosmos. A cluster of massive stars formed from a cloud of gas. Those stars lived brief, brilliant lives and died in catastrophic explosions. Those explosions carved out a vast cavity, compressed surrounding gas into dense walls, and triggered the formation of new stars along those walls. The Sun drifted into this cavity millions of years ago, finding itself in an unusually quiet corner of the galaxy. Life on Earth evolved during this period of relative calm, and now, that same life has developed the capacity to look outward, detect the bubble surrounding it, reconstruct its history, and begin to understand its place within it. Science has not yet determined whether the Sun's passage through the local bubble is connected in any causal way to the development of complex life on Earth. It may be pure coincidence, a cosmic accident with no deeper meaning. Or it may be that the stable environment provided by a low-density bubble is one of the conditions that allows intelligent life to arise and persist long enough to ask these questions. We do not yet have enough examples to know. But what we do know is that our understanding of the local bubble has advanced dramatically in just the last few years, driven by data from Gaia, by the ingenuity of researchers willing to do the difficult computational work of three-dimensional mapping, and by a willingness to look at familiar star-forming regions with fresh eyes and ask whether they might all be part of a larger, connected structure. The research teams working on the local bubble are not finished. They have laid out an ambitious roadmap that includes mapping additional superbubbles throughout the Milky Way, building a comprehensive three-dimensional model of the galaxy's bubble structure, and connecting that structure to the historical record of star formation rates across galactic time. By understanding when and where superbubbles formed, scientists hope to reconstruct the star formation history of the Milky Way with a level of detail that was impossible before Gaia. There is also work underway to better characterize the physical conditions inside the local bubble, the temperature and density of the hot plasma, the strength and topology of the magnetic fields threading through it, and the properties of the thin layer of warm neutral gas that lines portions of the bubble's interior. These measurements come from a variety of instruments operating across the electromagnetic spectrum, from soft X-ray satellites that detect emission from the hot plasma, to radio telescopes that map the distribution of neutral hydrogen. Each new observation adds another piece to the picture, and the picture that is emerging is of a cosmos that operates, at least in part, through a grand cycle of creation and destruction, stars dying to clear space, that cleared space filling with the compressed remnants of the explosion, those remnants becoming the next generation of stars. The local bubble is a snapshot of this process, caught mid-cycle with its former stars long gone, its walls alive with new star formation, and its interior providing temporary refuge to one particular star, and its small but curious family of planets. We have been asking, for as long as we have had the capacity to ask, whether we are alone in the universe. One underexplored dimension of that question is whether the cosmic environment shapes which worlds can sustain complex life over geological timescales. The local bubble adds a new layer to that inquiry. A solar system drifting through a dense molecular cloud or crossing a spiral arm filled with recent supernovae would face a very different cosmic history than one quietly orbiting near the center of a vast, swept-clean superbubble. Whether that difference is decisive for life, whether the local bubble is, as some researchers have poetically suggested, a kind of gift is a question that sits at the intersection of astrophysics, geology, evolutionary biology, and what we might simply call cosmic fortune. Science, by its nature, resists the language of gifts and fate. It prefers mechanisms and probabilities. And the mechanism here is clear. Supernovae happened, gas moved, space was cleared, and the sun drifted in. The probability side is harder to assess without knowing how many intelligent civilizations exist in how many different interstellar environments. But the question is worth taking seriously. And as astronomers continue to map the Milky Way's superbubble population, identifying and characterizing the dozens or hundreds of structures like the local bubble that are likely to exist throughout the galaxy, they will be building the statistical foundation needed to ask whether the quiet harbor we inhabit is rare, common, or somewhere in between. For now, what we can say with confidence is this: the space surrounding our solar system is not empty by chance. It was emptied by stellar violence millions of years before our species existed. Violence so complete and so sustained that it cleared a region of space 1,000 light-years across. Our sun drifted into that cleared region, and in the stability it offered, complex life on a small blue planet had the time and the conditions to evolve, to look up, and eventually to begin to understand the structure of the cosmos it inhabits. That is not a small thing to understand, and there is much more still to learn. Let us take a step further back and think about what it means to measure something as vast and diffuse as the interstellar medium. The challenge is not like measuring the temperature in a room or counting the grains of sand on a beach. The interstellar medium is spread across unimaginable volumes. It interacts with light in subtle ways that require careful calibration to interpret, and different components of it, hot plasma, warm ionized gas, cold neutral hydrogen, molecular clouds, are detectable only through completely different observational techniques. Some regions glow in visible light. Others are traceable only through radio waves. The very hot plasma in the local bubble's interior reveals itself in soft X-rays. The cold molecular gas on the bubble's surface is mapped through millimeter wave emission from carbon monoxide molecules, which form in abundance only in the coldest and densest parts of interstellar clouds. The fact that we have managed to assemble a coherent, three-dimensional picture of the local bubble at all is a testament to decades of painstaking observational work, clever theoretical modeling, and the development of increasingly powerful instruments. The Gaia spacecraft, with its ability to precisely locate and track the motions of over 1 billion individual stars, turned out to be the key that unlocked the bubble's three-dimensional structure. By mapping where young stars, the products of recent star formation, are located, and by measuring how those stars are moving, the researchers could identify the shell of the bubble and trace its expansion back through time. Young stars carry within them a kind of memory of the conditions in which they formed. Their positions tell us where the dense gas was concentrated when they were born. Their velocities carry the imprint of the shock waves and pressure gradients that set the gas in motion. By reading these imprints in a statistically large sample of young stellar objects, the research team was able to essentially watch the bubble's evolution, not in real time, which would require tens of millions of years of observation, but by reconstructing history from the current state of its contents. This kind of cosmic archaeology is one of the most powerful techniques in modern astrophysics. We cannot watch stars form and die over their full lifetimes, but we can observe large populations of stars and stellar remnants at different stages of their evolution, and from that statistical sample, we can reconstruct the life cycle of stars with confidence. The local bubble extends this approach to the scale of entire interstellar structures, using entire populations of young stars as tracers of the bubble's history. It is worth dwelling on the scale of the local bubble for a moment, because it is genuinely difficult to hold in mind without some points of comparison. 1,000 light-years across. Light, traveling at approximately 300,000 kilometers per second, the fastest speed possible in the universe, takes 1,000 years to cross the bubble from wall to wall. Our entire recorded human history, from the earliest written documents of Mesopotamia to the present day, covers only about 5,000 years. In the time it takes light to cross the local bubble, our civilization could rise and fall 200 times over. And yet the bubble itself, at 1,000 light-years, is a tiny feature of the Milky Way, which spans roughly 100,000 light-years from edge to edge. The Sun sits within this bubble at a distance of about 26,000 light-years from the galactic center. It is part of the Orion Arm, or local arm, a smaller spur between the two major adjacent spiral arms, the Sagittarius Arm on the inside and the Perseus Arm on the outside. The bubble spans a significant portion of the local arm, touching and overlapping with structures in both the adjacent arms. Some of the star-forming regions on its surface are actually part of the Sagittarius Arm and the Perseus Arm, which reinforces the idea that the bubble's expansion has physically influenced the gaseous structure of both arms. This spatial relationship between the local bubble and the spiral arms is one of the reasons scientists believe that the Milky Way's overall star formation history may be significantly driven by superbubble dynamics. The spiral arms of the galaxy are not solid structures. They are density waves, regions of slightly elevated density that propagate through the disk like a wave moving through a pond. As interstellar gas flows through a spiral arm, it gets compressed, and that compression helps trigger star formation. But supernovae add another layer of complexity to this process. When a generation of massive stars forms in a spiral arm and eventually explodes, the resulting superbubble can push the remaining gas outward, sometimes into the next spiral arm, where it may trigger another round of star formation. This creates what astronomers call a propagating star formation scenario, a kind of cascade where one generation of stars, by its violent death, sows the seeds of the next generation, and the whole process slowly ripples through the galaxy. The local bubble may be a particularly clear and well-mapped example of this process. The original massive stars of the Scorpius-Centaurus Association exploded, creating the bubble. The compressed gas on the bubble's walls is now forming new stars, including the clouds of Ophiuchus, Taurus, Perseus, and others. Some of those new stars will be massive enough to eventually go supernova themselves, potentially seeding new bubbles, new compressions, new star formation events millions of years from now. It is a cycle of destruction and creation operating over geological and evolutionary timescales, and we happen to live in the middle of one of its clearest examples. The universe, it turns out, is not chaotic or random at large scales. It has structure. It has pattern. And the local bubble is one of the most beautiful expressions of that pattern within reach of our telescopes. The question of how typical our situation is, how many solar systems are located in comparable bubble interiors at any given time, is one that researchers are beginning to address. It requires, first, a reliable census of superbubbles in the Milky Way. That census is not yet complete. We have identified the local bubble with high confidence because it is the one we can study in the most detail. Other known superbubbles include the Eridanus superbubble, the Orion superbubble associated with the Orion Nebula, and several others in varying directions around the sky. Each of these has its own size, age, expansion history, and relationship with the surrounding interstellar medium. As the data from Gaia continues to be analyzed, and as future missions extend the catalog of stellar positions and motions to greater distances, the number of mapped bubbles will grow. There are already hints from X-ray sky surveys and radiohydrogen surveys that the structure of the Milky Way's interstellar medium is dominated by a network of interconnected bubbles and shells rather than a smooth, uniform medium. The Swiss cheese analogy offered by the Harvard-Smithsonian team may be more accurate than metaphorical. The galaxy's disk, viewed in the right way, may look more like a frothy foam of nested and overlapping shells than like a uniform expanse of gas and stars. This frothy structure has important implications for how efficiently a galaxy converts its gas supply into stars. If the interstellar medium were smooth and uniform, star formation would depend entirely on the self-gravity of individual clouds. But in a Swiss cheese medium, the dynamics are much richer. Bubbles expand and collide, shells compress and fragment. Gas evacuated from one region is pushed into another. The resulting star formation rate is higher and more spatially structured than a smooth medium would produce. Models that incorporate this bubble structure into galactic simulations do a better job of reproducing the observed properties of real galaxies, their star formation histories, their spiral structures, and their overall gas content. So the local bubble is not just an interesting local curiosity. It is a key piece of evidence in our understanding of how galaxies work as systems. Consider also what the local bubble has done for our ability to see the universe at all. This may sound like a strange thing to say after all. Whether we are inside a bubble or not, we still have telescopes that can observe distant galaxies. But the interstellar medium between stars scatters and absorbs light, particularly in the ultraviolet and X-ray parts of the spectrum. A dense, dusty interstellar medium would significantly impair our ability to observe certain types of astronomical phenomena. Inside the local bubble, the low-density, low-dust environment means that our view of the galaxy and the broader universe, in many wavelengths, is cleaner than it would be if the sun were located in a typical interstellar environment. This is particularly true for ultraviolet astronomy. Ultraviolet light is absorbed very efficiently by interstellar dust and neutral hydrogen. A telescope operating in the ultraviolet wavelengths can see much further from within the local bubble's near vacuum than it could from within a region of normal or elevated interstellar density. The same is true for soft X-ray astronomy. Many of the X-ray observations that have revealed the properties of hot plasma in the local universe would have been significantly compromised if the sun were embedded in denser, interstellar material. In other words, we may be especially well positioned not only to survive in the cosmic environment, but also to observe it. The bubble that protects us also provides us with an unusually clear window onto the universe. That double role, cosmic shield, and observational vantage point makes the local bubble feel, from the human perspective, like something almost impossibly well designed. Of course, it is not designed at all. It is the product of purely physical processes operating on enormous scales over enormous timescales. But it is striking nonetheless. As astronomers map more superbubbles and compare their properties, one of the things they will be looking for is whether other bubbles, ones that may contain other solar systems with potentially habitable planets, are similar enough to ours to provide comparable protection and visibility. This is a genuinely new frontier in astrobiology, the study of the conditions that allow life to arise and persist. Most astrobiological research focuses on the immediate environment of individual planets, their distance from their star, their atmospheric composition, the availability of liquid water. But the cosmic environment at the galactic scale matters too. A planet in the right zone around the right kind of star, but located in a dense molecular cloud, or in the heart of a star-forming region with frequent nearby supernovae, may face insurmountable challenges for the long-term stability of complex life. The local bubble, from this perspective, is a sample size of a single data point in what would need to be a much larger statistical study to draw firm conclusions. But it is a data point that exists, that is measurable, and that invites us to ask a question that astronomy has rarely posed so directly. Does the large-scale structure of the interstellar medium influence habitability? The answer is almost certainly yes, to some degree. How much, and over what timescales, are questions that the next generation of observations and models will be better positioned to address. Meanwhile, the science of the local bubble continues to develop rapidly. The three-dimensional mapping effort is ongoing. New papers appear regularly, adding detail to our understanding of the bubble's shape, the properties of its star-forming wall, and the history of the supernovae that created it. The iron-60 deposits in Earth's crust are being studied more carefully, with isotopic analyses that can potentially distinguish the contributions of different supernova events at different distances. Theoretical simulations of the bubble's formation are being refined with better input physics. All of this work is part of a broader revolution in our understanding of the Milky Way that is being driven primarily by Gaia. Before Gaia, we had good two-dimensional maps of the sky, excellent catalogs of where stars appear when projected onto the celestial sphere. But three-dimensional mapping, with accurate distances and proper motions for hundreds of millions of stars, was beyond reach. Gaia changed that. In the few years since it began releasing data, it has transformed almost every branch of stellar and galactic astronomy, including the study of the local bubble. The future holds even more. Surveys like the Rubin Observatory's Legacy Survey of Space and Time, set to become operational in the coming years, will extend the census of stars, variable objects, and interstellar medium tracers to greater depths, and with higher time resolution than ever before. The Square Kilometer Array, a radio telescope of unprecedented collecting area, will map neutral hydrogen across the Milky Way and nearby galaxies with extraordinary sensitivity. Together, these instruments will build on the foundation laid by Gaia to produce a comprehensive picture of our galaxy's structure and evolution. And as our maps improve, our understanding of our own position within the galaxy will sharpen. We will be able to determine, with greater precision, exactly where the walls of the local bubble are, what is beyond them, and how our passage through this remarkable structure compares to the broader history of the Sun's galactic orbit. We may find that the Sun has passed through similar bubbles before, leaving traces in the geological record that we have not yet learned to read. We may find that the current period of relative calm is unusually extended, or quite typical. We may find signatures in Earth's climate record, in the distribution of impact craters, or in the genetic record of life's evolutionary history that connect the cosmic environment to events on our planet in ways we have not yet imagined. What the local bubble has already given us is a new way of thinking about ourselves in the universe. Not as observers looking out from a fixed, unremarkable point, but as travelers moving through a structured cosmos, currently passing through a remarkable cleared space that has shaped the conditions for our existence in ways we are only beginning to understand. The story of the local bubble is, in part, our own story, a story of stellar violence, galactic drift, and the long, improbable, beautiful chain of events that led to curious beings on a small planet, looking up at the stars and asking where they are. The answer, it turns out, is inside a bubble, a very big bubble, one created by dying stars, shaped by cosmic physics, and home, for now, to everything we have ever known. Now, to truly grasp what makes all of this significant, it helps to understand just how exceptional it is that we can reconstruct any of this story at all. We are talking about events that happened 14 million years ago, at distances of hundreds to thousands of light years, in a medium so tenuous that most instruments would register it as pure vacuum. Yet through a combination of clever physics, patient observation, and computational ingenuity, scientists have managed to piece together a detailed history of cosmic violence and renewal, and to place our own solar system within it. Let us think about how stars actually form on the surface of the local bubble, because the process is elegant and deeply connected to everything we have been discussing. When a supernova shockwave expands outward through the interstellar medium, it does not push the gas aside uniformly. The interstellar medium is not smooth, it is clumpy, with denser knots and filaments embedded in a more diffuse background. When the shockwave hits a particularly dense clump of gas, something interesting happens. Instead of being pushed along as a unit, the clump gets compressed from one side. The shockwave squeezes it, increases its density, and potentially pushes it over the threshold where gravity can take over. Gravity has always been acting on that gas cloud, but interstellar clouds are supported against self-gravity by a combination of thermal pressure, magnetic fields, and turbulent motions. When a shockwave increases the density sufficiently, the gravitational pull between the cloud's constituent atoms and molecules can overcome these support mechanisms. The cloud begins to collapse inward. As it collapses, it heats up just as compressing any gas releases heat. Eventually, if the cloud is massive enough and dense enough, the temperature at its center rises to the point where hydrogen fusion can ignite. A new star is born. This is exactly what is happening along the surface of the local bubble right now. The 7 star-forming regions identified in the Harvard-Smithsonian study are all in various stages of this process. Some contain newly formed protostars objects that are collapsing but have not yet reached fusion ignition. Others contain young stellar objects that have just started fusing hydrogen in their cores. Still others contain slightly older young stars surrounded by disks of gas and dust from which planets are currently forming. The Ophiuchus molecular cloud complex, located about 450 light-years away, is one of the most active star-forming regions in the solar neighborhood. It contains hundreds of young stellar objects in various stages of formation, embedded in a rich complex of gas and dust. The Taurus molecular cloud, slightly closer at around 430 light-years, is another active nursery known particularly for producing lower mass stars like our Sun, surrounded by well-studied protoplanetary disks. Both of these regions sit on the surface of the local bubble. Their existence and the current star formation happening within them is a direct consequence of the same supernovae that carved out the bubble. The dying stars of millions of years ago are, in a very real sense, the parents of the stars being born today in Ophiuchus and Taurus. This cosmic parentage extends to planetary systems. When a molecular cloud collapses to form a star, the collapsing material typically has some angular momentum. It is rotating slightly, perhaps due to turbulent flows in the original cloud. Conservation of angular momentum causes the collapsing cloud to spin faster as it shrinks, just as a spinning ice skater accelerates when pulling in their arms. The result is that the material does not all fall directly onto the forming star. Instead, it flattens into a rotating disk around the young star. That disk is called a protoplanetary disk, and it is the birthplace of planets. Over millions of years, the gas and dust in a protoplanetary disk gradually clump together through collisions and gravitational attraction. Small particles stick together to form pebbles. Pebbles aggregate into boulders. Boulders accumulate into planetesimals, and planetesimals eventually grow into planets. The process is messy, violent, and involves tremendous amounts of material being scattered, ejected, and occasionally impacting already formed planets. But the end result, in enough cases, is a planetary system. Some of the young stars currently forming in the star-forming regions on the local bubble's surface will acquire planetary systems. Some of those planets will be in the habitable zone, the range of distances from the star where liquid water can exist on a surface. And some small fraction of those habitable zone planets, perhaps, will develop life. Whether any of them will produce beings capable of looking back at the local bubble and wondering about their place in it, that is a question for a future science, a future intelligence, in a future that is currently being born, quite literally, on the walls of the bubble surrounding us. There is something profound in that image. The local bubble is not just our home. It is a nursery for future homes. The stars being born on its surface today are the suns of other, future solar systems. Some of those systems may be habitable, and they will owe their existence, at least in part, to the same supernovae that carved out the space our sun now occupies. The universe recycles everything: matter, energy, even the preconditions for life. The local bubble is a single frame in an enormously long film of cosmic recycling, and we are fortunate enough to be watching at a moment when we have developed just enough understanding to recognize what we are seeing. One more aspect of the local bubble deserves attention before we turn to the current frontier of research, and that is the question of the bubble's future. What will happen to it over the coming millions of years? The bubble is currently expanding at roughly 4 miles per second, about 6 to 7 kilometers per second. That sounds fast by human standards, but by the standards of interstellar processes, it is quite slow. At this rate, the bubble grows by about 1 light-year of radius every 40,000 years or so. Over the next million years, it might expand by roughly 25 light-years in radius. Over the next 10 million years, perhaps 250 light-years. This is modest compared to its current size of 500 light-years in radius. More importantly, the energy driving the expansion is not being replenished. The supernovae that created the bubble are long past. The hot plasma inside the bubble is slowly cooling, not at a rate that is immediately dramatic, but over millions of years, the thermal pressure that has been driving expansion will continue to decrease. At some point, the bubble's expansion will essentially stall. The pressure inside will equalize with the pressure outside. The bubble will no longer grow. At that point, one of several things can happen. The bubble might simply sit there, gradually being eroded from the outside as it mixes with the surrounding interstellar medium. It might be disrupted by a nearby supernova, either one that occurs inside the bubble, re-energizing it, or one that occurs outside, sending a new shockwave through the structure. Or the sun might drift out of the bubble on its own, simply moving beyond the cavity's boundary as it continues its orbit around the galactic center. That last scenario, the sun exiting the local bubble, will almost certainly happen eventually. The sun moves at roughly 220 kilometers per second around the galactic center, and through the local standard of rest, the average motion of nearby stars, it is also drifting slowly. In a few tens of millions of years, depending on exactly how large the bubble becomes, and exactly how the sun's trajectory carries it, the sun will likely move back into a region of higher interstellar density. At that point, the heliosphere will be compressed from outside by denser interstellar medium. Its radius will shrink. Its protection of the inner solar system may be reduced, and the cosmic ray flux reaching Earth could increase. Whether that transition, when it occurs, will have measurable effects on Earth's biosphere is unknown. The changes would be gradual by human standards, taking place over hundreds of thousands to millions of years. Life on Earth has survived similar transitions before, if the correlations with spiral arm crossings and mass extinctions are real, but survival does not mean unchanged. The pressures of a different cosmic environment might reshape evolution in ways that are simply impossible to predict. For now, though, we are inside, floating near the center of a 1,000 light-year bubble of near vacuum, surrounded by newly forming stars, protected from cosmic rays by both the bubble itself and by the sun's own heliosphere, gazing outward into a universe we are only beginning to understand. The science of the local bubble is young. The three-dimensional mapping is still being refined. The connections between the bubble's structure and Earth's geological history are still being investigated. The theoretical models of how exactly the supernovae formed it, how it interacts with its neighbors, and what its future holds are still being improved. There are more questions than answers in almost every direction you look within this field. That is the nature of good science. Every answer opens 3 new questions. Every observation adds a piece to the puzzle and reveals the edges of 3 more pieces waiting to be found. The local bubble is no exception. In some ways, we know more about it today than we have ever known. In other ways, we are only just beginning to understand what questions to ask. What we can say with confidence is that our position in the universe is not random in any simple sense. The sun is where it is because of a specific sequence of cosmic events, star formation, stellar evolution, supernova explosions, galactic dynamics, and 14 million years of expansion and drift. Understanding those events is understanding, in a deeper way than most of us usually consider, the conditions of our own existence. There's a version of this story that ends with a kind of cosmic vertigo, the realization that we are tiny, temporary, and cosmically insignificant. And there's another version that ends with something closer to wonder, the realization that the cosmos is deeply structured, that those structures connect to our existence in ways we can trace and measure and understand, and that we are, for whatever reason, in a particularly remarkable spot from which to observe all of it. The local bubble does not resolve that tension, but it deepens it beautifully. We are inside a vast, ancient, slowly dying bubble, blown by long-dead stars, surrounded by the nurseries of stars yet to be born, drifting in the quiet aftermath of violence, looking outward in every direction with the instruments of curiosity. And the universe, it turns out, has been busy all along, carving holes, compressing walls, igniting new suns, cycling matter through death and rebirth across timescales that make human history seem like the blink of an eye. The bubble is 1,000 light-years across. It has been expanding for 14 million years. The sun wandered into it 5 million years ago. And we, the inheritors of all of that cosmic history, have been here for only the last 200,000 years, which is less than 1/100% of the time the bubble has existed. Yet in that tiny fraction of the bubble's life, we have managed to figure out that we are inside it. That, perhaps, is the most remarkable thing of all. Let us now take a closer look at some of the specific measurements and observations that have made this science possible, because the story of how we discovered the local bubble is itself as fascinating as the discovery itself. The first hints came from X-ray astronomy. In the 1970s, early X-ray satellite missions, the kinds of instruments strapped to rockets and flown briefly above Earth's atmosphere before high-altitude observatories became possible, detected a diffuse glow of soft X-rays coming from all directions in the sky. This was unexpected. X-ray emission from individual exotic objects like neutron stars and black holes was known and theoretically understandable, but a smooth, diffuse background of soft X-rays filling the whole sky suggested something different. It suggested that the sun was embedded within a large volume of extremely hot, tenuous plasma heated to temperatures of around 1 million degrees Celsius. At 1 million degrees, even the lightest gas emits X-rays. The plasma in the local bubble's interior is hot enough to emit in the soft X-ray band because the supernovae that created it deposited enormous amounts of thermal energy into the gas, and that gas, being so thin, has no efficient mechanism to radiate that energy away quickly. It cools slowly. Over millions of years, it gradually loses energy, but the cooling timescale is long enough that the bubble's interior is still glowing faintly in X-rays today, a fading echo of the violence that created it. This discovery established that something unusual was happening in our immediate galactic neighborhood, but it was difficult to interpret without better distance information. Were we seeing a hot bubble that was specifically local a few hundred light years across? Or were we seeing emission from much larger scale structures further afield? The answer required better three-dimensional maps. Those maps came from studies of neutral hydrogen absorption. Neutral hydrogen absorbs ultraviolet light very efficiently. If you have a star at a known distance and you observe it through a cloud of neutral hydrogen, you can measure how much ultraviolet absorption occurs and therefore estimate how much hydrogen lies between you and the star. By doing this for stars at many different distances, in many different directions, astronomers began to build a picture of where the hydrogen was, and crucially, where it was absent. What they found was that within a few hundred light years of the sun in most directions, the density of neutral hydrogen was anomalously low. Stars within this region showed little or no interstellar absorption. Stars beyond a few hundred light years showed much stronger absorption, indicating that they were behind a wall of denser material. This technique provided some of the first direct evidence of the bubble structure, a roughly spherical region of cleared gas surrounding the sun. Later observations refined this picture considerably. The Rosset X-ray satellite, launched in 1990, provided the most detailed all-sky map of soft X-ray emission up to that point, confirming the large-scale structure of the hot plasma bubble and revealing fine-grained structure within it. Subsequent X-ray observatories, including XMM Newton and Chandra, have been used to study specific directions and specific distances within the bubble in more detail. The sodium deabsorption line, a doublet of spectral lines visible to optical telescopes, became another key diagnostic tool. Interstellar sodium absorbs starlight at very specific wavelengths, and the strength of that absorption tells you how much sodium, and by proxy, how much interstellar medium lies between you and a star. Surveys using this technique built up a picture of the bubble's neutral gas content from the inside out, star by star. By the early 2000s, enough data had accumulated that it was possible to construct rough three-dimensional models of the local interstellar medium, showing the bubble-like structure surrounding the sun with higher density material starting somewhere between 100 and 300 light years away in most directions. But these models were limited by the accuracy of stellar distance measurements. Without precise distances to the stars being used as absorption probes, the three-dimensional structure was blurry and poorly constrained. This is precisely where Gaia changed everything. Gaia measures stellar parallaxes, the tiny shifts in apparent position of nearby stars as Earth orbits the sun, with an accuracy that was previously unimaginable from ground-based observatories. From stellar parallaxes, you get distances. With distances, you can place every star precisely in three-dimensional space. And with precise three-dimensional positions, you can convert the two-dimensional absorption maps into genuine three-dimensional density maps of the interstellar medium. The result is the most detailed three-dimensional map of the local interstellar medium ever produced. It shows not just the bubble, but its interior structure, its wall, the molecular clouds embedded in that wall, and the connections between those clouds and the young stars they have produced. It is, in a sense, the first time we have had a true bird's-eye view, or rather, a cosmological view from outside of the structure that surrounds us. The research team that assembled this map took the additional step of placing young stellar clusters at their correct three-dimensional positions and tracing their motions backward in time. By running the clock backward, they could determine where those clusters were when their stars first formed, and all of those formation locations lie on or near the surface of the expanding bubble. It is extraordinarily compelling evidence that the bubble and the star formation on its surface are causally connected, not merely spatially coincident. One of the more subtle but important aspects of this work is what it implies about the timing of star formation in the solar neighborhood. We can ask, when did the molecular clouds on the bubble's surface first start forming stars? The answer, based on the ages of the young stellar clusters, appears to be a few million to a few tens of millions of years ago, consistent with the idea that the bubble's expansion triggered the compression that led to star formation. The timing works out. The bubble created the conditions led to collapse, and the collapse is producing stars that we can observe today. This kind of coherent, causal, multi-step story, where every piece fits together physically and chronologically, is what scientists mean when they talk about a model being not just consistent with data, but genuinely explanatory. It is a higher standard than mere correlation, and the local bubble, at this point, meets it. The story extends outward too, into what we might call the bubble's context within the broader galaxy. The Milky Way, when viewed in 3 dimensions using Gaia data, shows a complex network of stellar streams, moving groups, and associations that trace the history of star formation across the galaxy over the past several hundred million years. The Scorpio-Centaurus Association, the stellar cluster most closely associated with the supernovae that created the local bubble, is part of this larger picture. It is itself the product of a previous generation of star formation, which was itself triggered by even earlier supernovae and bubble expansions. Going further back in the chain, we find that the sun's path through the galaxy has taken it through several different environments over the 4.6 billion years since it formed. There have been periods of higher interstellar density, the spiral arm crossings, and periods of lower density between the arms. The current period, inside the local bubble, may be one of the most sheltered the sun has experienced in hundreds of millions of years. Or it may be relatively typical of the interarm regions. With better three-dimensional models of the Milky Way's past structure, it may eventually be possible to reconstruct the sun's complete environmental history, reading it like a ship's log of cosmic travel. Each environment the sun passed through has potentially left traces not just in the geological record, but in the distribution of Kuiper belt objects, in the inclinations and eccentricities of outer solar system bodies, in the chemistry of ancient meteorites, and in the isotopic signatures preserved in Earth's crust. Connecting all of these dots is a scientific project that will take decades, but the local bubble is a crucial anchor point, the most recent and most clearly mapped chapter in the sun's galactic biography. It is also worth noting that the solar system's relationship with the local bubble is not simply one of passive inhabitancy. The sun contributes to the bubble's interior through the solar wind, the constant outflow of charged particles that creates the heliosphere. The heliosphere is, in a sense, the sun's own tiny bubble nested inside the larger one, and the heliosphere interacts dynamically with the bubble's interior plasma. As the sun and its heliosphere move through the local bubble's interior, they push through the thin ambient plasma of the bubble. This creates a bow shock ahead of the heliosphere, a region where the bubble's plasma is piled up and heated as the heliosphere sweeps through it, somewhat like the wave pushed ahead of a moving boat. The properties of this interaction depend on the density and magnetic field of the bubble's plasma, quantities that are still being measured and modeled. There is ongoing scientific debate about exactly how the boundary of the heliosphere responds to changes in the surrounding interstellar medium. If the sun moves through a denser patch of the bubble's plasma, perhaps as it drifts toward the bubble's wall, the heliosphere would be compressed. Its radius would shrink. The protection it offers to the inner solar system would diminish. There is evidence, From measurements of heliospheric hydrogen by the Voyager probes and by Earth-orbiting instruments, that the interstellar medium immediately surrounding the heliosphere has changed slightly in density even over the past few decades. These are small fluctuations, but they hint at the dynamic nature of the boundary environment. On longer timescales, as the Sun approaches the bubble's wall and eventually enters the denser surrounding medium, the heliosphere's compression could be significant. Theoretical models suggest that in a very dense interstellar cloud, the heliopause could be pushed in to within a few astronomical units of the Sun, well within the orbit of the outer planets. Under those conditions, cosmic rays that are currently deflected by the heliosphere would penetrate much deeper into the solar system. The Earth's radiation environment would change. Whether this would be immediately harmful to life is debated, but it would represent a meaningfully different state of cosmic exposure. Fortunately, that scenario is not imminent. The Sun is currently near the center of the bubble, moving at speeds that will keep it in the low-density interior for millions of years to come. The heliosphere is near its maximum comfortable extent, and we, on Earth, are shielded by both the heliosphere and the bubble's cleared interior. All of this, the two-bubble architecture of cosmic protection, the star-forming nurseries on the bubble's walls, the connections between supernova history and geological events on Earth, the ongoing research to map and understand the structure, forms a coherent and increasingly well-supported picture of our local cosmic situation. It is a picture that was essentially invisible to us 50 years ago, and that has come into focus through a remarkable confluence of technological capability, theoretical ingenuity, and the patient accumulation of observational data. What will the picture look like 50 years from now? Some things are predictable. The Gaia mission will complete its full data releases, providing the deepest and most precise stellar catalog in history. New X-ray observatories will improve our view of the hot plasma filling the bubble. Radio surveys will map the neutral and molecular gas on the bubble's surface with higher resolution. Simulations of the bubble's formation and evolution will become more sophisticated as computing power grows. But science also has a way of producing surprises, unexpected observations that overturn established models, or that reveal structure and connection where none was suspected. The local bubble might turn out to be connected to other superbubbles in ways that create larger-scale patterns we have not yet recognized. The iron-60 deposits in Earth's crust might, with further analysis, reveal a more complex and detailed chronology of nearby supernova activity than current data suggests. The relationship between the bubble's history and Earth's evolutionary history might turn out to be more profound, or alternatively, more incidental than current thinking suggests. And there is always the possibility of a discovery so fundamental that it changes the entire framing of the question. Science is full of moments like that. Moments when a new piece of data or a new theoretical insight reorganizes everything that came before it and reveals a deeper order that was always there, waiting to be found. The local bubble is a story still being told. Its ending is not yet written. But the fact that we are telling it at all, that creatures on a small planet recently descended from the trees, we have figured out that they are inside a 1,000 light-year bubble blown by stellar explosions 14 million years ago, is extraordinary. It is one of the most remarkable things our species has ever done. And it is, in the best tradition of science, just the beginning. To understand why the local bubble matters so deeply as a scientific discovery, it helps to think carefully about what it actually means to be inside a superbubble, not in an abstract sense, but in the concrete, physical sense of what your environment is, and how it differs from the galactic average. Start with the numbers. The average density of the interstellar medium in the disk of the Milky Way, counting all phases of the medium, from cold molecular gas to warm ionized plasma, works out to roughly 1 atom per cubic centimeter. Inside the local bubble's hot interior, the density is closer to 0.005 atoms per cubic centimeter. That is 200 times less dense than the galactic average. 200 times less material per unit volume. Those are abstract numbers, so let us make them more tangible. Imagine filling a box, 1 meter on each side, roughly the size of a large aquarium, with interstellar medium from a typical region of the galaxy. In that box, you would have, on average, 1 million cubic centimeters of space, each containing 1 atom. so 1 million atoms total. If you took that same box and filled it with the interior of the local bubble, you would have only about 5,000 atoms. The difference between a packed theater and a nearly empty one. Now imagine that difference extended across thousands of light years. The sheer volume of material that was moved, pushed outward from what is now the bubble's interior to its compressed walls, represents an almost incomprehensible amount of mass redistribution. The wall of the local bubble contains this swept-up material, compressed into dense molecular clouds that are, right now, actively converting that ancient swept-up gas into new stars. The energy budget is equally staggering. Each supernova releases roughly 10 to the power of 44 joules of energy. With approximately 15 supernovae contributing to the local bubble's formation, the total energy input was around 1.5 times 10 to the power of 45 joules. Written out in words, that is 1.5 octillion joules, a number so large it defies everyday intuition. For comparison, the entire nuclear arsenal of Earth, if detonated simultaneously, would release something like 5 times 10 to the power of 18 joules, roughly 26 million times less energy than a single supernova. This energy did not all go into moving gas. A significant fraction went into radiation, the blinding light of the explosion itself. A significant fraction went into accelerating particles to relativistic speeds, creating the cosmic rays that still stream through our galaxy. A fraction heated the gas to millions of degrees, and a fraction went into the kinetic energy of the expanding shell, the actual mechanical work of pushing interstellar material outward. The fact that the bubble is still expanding, still warm, and still detectably different from the surrounding medium after 14 million years tells us that the energy deposited was genuinely enormous. The cooling and equilibration timescales for hot, low-density plasma are very long, much longer than for dense, cold gas. The local bubble is, in this sense, still digesting its violent past. This is also why the bubble's interior is X-ray bright. Hot plasma at 1 million degrees Celsius emits most of its energy in the form of soft X-rays photons, with energies between about 0.1 and 10 kilo-electron volts. For the bubble's plasma, the dominant emission mechanisms are thermal Bremsstrahlung, the radiation produced when charged particles accelerate as they pass near each other, and line emission from partially ionized atoms of oxygen, carbon, silicon, and other elements. These emission lines carry detailed information about the temperature and composition of the plasma, and they have been used by X-ray astronomers to characterize the bubble's interior since the 1970s. More recent X-ray observations have added important nuance to this picture. The Rosat All-Sky Survey, and later surveys by XMM Newton and other observatories, revealed that the X-ray emission from the bubble's interior is not perfectly uniform. There are brighter patches and dimmer patches. Some of this variation reflects inhomogeneity in the bubble's plasma density. Some may reflect variations in the line of sight distance to the bubble's wall, and some may reflect the presence of small, dense cloudlets, knots of cooler, denser gas that survived the supernova shockwaves and are now embedded in the hot interior like islands in a warm sea. These cloudlets are scientifically interesting because they represent material that was not fully destroyed or swept up by the supernova shockwaves. They may carry a record of the pre-bubble interstellar medium, a snapshot of what the local galaxy looked like before the explosions began. Studying their chemistry and kinematics could provide information about the conditions in the solar neighborhood before the first of those 15 supernovae detonated 14 million years ago, before the bubble existed at all. The interplay between the bubble's hot interior plasma and these cool cloudlets is also a laboratory for studying thermal conduction and evaporation in plasmas. When a cool cloud is embedded in hot plasma, heat conducts from the plasma into the cloud. The cloud's outer layers evaporate, feeding mass back into the hot medium. The rate at which this happens depends on the temperature and density of both the cloud and the surrounding plasma, and on the strength and geometry of the magnetic fields threading through the region. By observing real cloudlets in real bubbles, astronomers can test theoretical models of these physical processes in ways that are impossible to replicate in terrestrial laboratories. Moving outward from the bubble's interior, we reach the transition zone, the region where the hot, tenuous plasma of the bubble's interior gives way to the cooler, denser gas of the bubble's wall. This transition is not sharp like a soap bubble's surface. It is a broad zone of mixing and turbulence, where hot plasma from the bubble's interior is eroding the edges of the wall, and where cooler gas from the wall is evaporating into the interior. The transition zone is also where much of the magnetic field structure threading through the bubble is concentrated, and where the density and temperature gradients are steepest. Observing this transition zone is technically challenging because different parts of it emit at different wavelengths. The hottest portions are visible in X-rays. The intermediate temperature portions emit in the ultraviolet. The cool outer portions are visible in optical and infrared light, and the coldest molecular parts of the wall emit at millimeter and radio wavelengths. A complete picture of the bubble's wall requires observations across this full electromagnetic spectrum, and pulling together data from instruments that operate in completely different regimes is a significant observational and data analysis challenge. The Harvard-Smithsonian team's three-dimensional reconstruction was particularly powerful because it did not rely solely on emission from the gas itself. Instead, it used the positions and motions of young stars' objects, whose distances can be precisely measured by Gaia, as tracers of the bubble's wall. Young stars form in dense gas and therefore mark the locations of that gas. By identifying where young stars are clustered and measuring their systematic motions outward, away from the bubble's center, consistent with being on the expanding wall, the team could define the wall's position and trace its shape across the sky. The result was a bubble that is not perfectly spherical. Real superbubbles never are. The interstellar medium they expand into is not uniform, and the bubble's expansion proceeds faster in directions where the surrounding medium is less dense, and slower where it encounters denser material. The local bubble shows this expected asymmetry. It is elongated in some directions and compressed in others, reflecting the non-uniform structure of the pre-bubble interstellar medium. One particularly interesting feature of the bubble's shape is that it appears to be open at the top and bottom, meaning it is not fully enclosed in the directions perpendicular to the galactic disk. The Milky Way's disk is thin compared to its diameter, and beyond the disk, the density of the interstellar medium drops rapidly. When a superbubble expands in the disk, it eventually breaks through the disk's surface and vents hot plasma out into the galactic halo, the vast diffuse region above and below the galactic plane. This blowout creates what astronomers call a galactic chimney, a column of hot plasma rising from the disk into the halo. There is evidence that the local bubble has created such chimneys. The soft X-ray emission from the bubble's interior appears to connect with broader structures of hot plasma that extend above and below the galactic plane. These structures may be part of a larger-scale circulation system for hot gas in the Milky Way, where supernovae in the disk heat and expel gas into the halo, and where that gas eventually cools and falls back down to replenish the disk's gas supply. This galactic fountain model has been proposed as an important mechanism for regulating star formation in galaxies, and the local bubble may be providing us with one of the best local examples of it in action. The galactic fountain process is important for the chemical evolution of galaxies as well. When supernova-enriched gas is expelled into the halo and then rains back down onto the disk, it distributes heavy elements more broadly through the galaxy's gas supply than simple radial mixing within the disk could accomplish. The freshly synthesized metals, iron, oxygen, silicon, magnesium, and the rest of the periodic table's middle sections get transported vertically, spreading through the halo and then settling back into the disk at different radii. This vertical mixing is an important ingredient in models of galactic chemical evolution, and the local bubble's chimneys may be contributing to it on a local scale today. Let us also think about what the local bubble means for the Fermi paradox. The famous puzzle of why, if the galaxy is filled with potentially habitable worlds, we have not detected any signs of extraterrestrial civilization. This is a well-known puzzle with dozens of proposed solutions, and the local bubble adds an interesting dimension to one class of them. One proposed resolution to the Fermi paradox is that civilizations are rare not just because the conditions for life are rare, but because the conditions for the long-term survival and technological development of intelligent life are rare. Even if simple life arises frequently, the step from simple life to a technological civilization capable of interstellar communication requires billions of years of relatively stable evolution, and that stability may be much harder to maintain in some parts of the galaxy than others. The spiral arm crossings and their associated mass extinctions suggest that periods of intense cosmic radiation and climatic disruption can wipe out significant fractions of the biosphere, potentially resetting evolutionary trajectories that had been building toward complexity. If technological intelligence requires not just the right initial conditions on a planet, but also an extended period of cosmic stability, something like what the local bubble may have provided over the past several million years, then the number of worlds that can produce technological civilizations at any given time might be much smaller than the number that could host life in principle. This is speculative, but it is a scientifically motivated speculation, grounded in real physics. The local bubble matters for the Fermi paradox not because it definitively solves it, but because it illustrates a category of factors, cosmic environmental stability, that is rarely accounted for in simple estimates of the probability of technological civilization. The Drake equation, in its classic form, asks about the rate of star formation, the fraction of stars with planets, the fraction of those with habitable planets, the fraction of habitable planets where life arises, the fraction where intelligent life arises, the fraction where technology develops, and the lifetime of technological civilizations. What it does not explicitly include is a term for the cosmic environment at the galactic scale, the likelihood that a given solar system will spend an extended period in a low radiation, low disruption environment. Adding such a term would reduce the expected number of contemporary technological civilizations. How much it would reduce it depends on factors we are still measuring. The local bubble is, in this sense, part of the answer to one of the deepest questions we can ask. Not the complete answer, but a piece of it. One more constraint on the conditions that made our existence possible. And as we map more of the galaxy's bubble structure and better understand the statistical distribution of these environments, we will be able to refine that constraint further. Meanwhile, the research teams working on the local bubble are focused not on such grand philosophical questions, but on the more immediate scientific ones. How exactly did the bubble form? Can we identify the specific stellar remnants, the neutron stars, and possibly black holes left behind by the supernovae that created it? Can we trace the detailed history of star formation on the bubble's surface and connect it to the formation of specific young clusters? Can we extend the bubble's map to include structures that may have been overlooked because they were too faint or too complex to resolve with earlier data? These are tractable questions, with specific observational programs being designed to address them. Neutron stars formed by supernovae can be detected as pulsars, rapidly rotating neutron stars that emit beams of radio waves that sweep past Earth like a cosmic lighthouse. If the supernovae that created the local bubble left behind neutron stars, those neutron stars should still be in the vicinity of the bubble, though they may have been kicked to high velocities by the asymmetries in the explosions, and may have drifted far from where the original star was. Pulsar surveys are already cataloging neutron stars in the local galaxy, and future radio telescope arrays will extend this catalog dramatically. Identifying specific pulsars that have the right kinematics to have originated in the bubble-forming supernovae is a challenging but potentially achievable goal. The chemical signatures of the local bubble supernovae may also be detectable in new ways. Different types of supernovae produce different ratios of isotopes. By looking at the specific pattern of radioactive isotopes found in Earth's geological record, not just iron-60, but also aluminum, 26, manganese-53, and other supernova products, researchers may be able to distinguish the contributions of individual supernovae and place tighter constraints on how many there were, how massive the progenitor stars were, and how far away they exploded. This kind of isotopic detective work is already underway. Several research groups are analyzing ancient deep-sea sediment cores and Antarctic ice cores, looking for the characteristic radioactive signatures of past supernova events. These cores preserve a time-sequence record of the cosmic ray flux and particle deposits that reached Earth over millions of years. The pattern of iron-60 peaks already suggests multiple distinct events rather than a single continuous exposure. With higher resolution isotopic analyses and more sophisticated atmospheric and oceanic models to account for how the supernova ejecta were transported from space to the ocean floor, the historical record of the bubble's supernovae may become much more detailed. The connection between the local bubble and the history of life on Earth is therefore likely to grow stronger and more nuanced as both the geological data and the astrophysical models improve. We may eventually be able to say, with some confidence, exactly when specific supernovae occurred, how far away they were, what fraction of their energy reached Earth's atmosphere, and what effects that energy had on the isotopic composition of the atmosphere, the surface radiation environment, and ultimately, the evolutionary pressures acting on life. That would be a remarkable achievement, reading the fossil record of distant explosions in the chemistry of ancient ocean sediments and connecting them to the structure of the bubble of space that surrounds us today. Science at its most interconnected and its most ambitious. We live in a remarkable time for this science. Instruments that would have seemed fantastical a generation ago are now operational and returning data. Computational power that would have required a building-sized supercomputer in the 1980s is now available on a laptop. The global scientific community shares data and ideas across borders and institutions in ways that would have been logistically impossible before the internet. All of these developments compound on each other, accelerating the rate at which our understanding grows. The local bubble is a beneficiary of all of this progress. It sits at the intersection of multiple rapidly advancing fields: stellar astronomy, interstellar medium physics, galactic dynamics, X-ray astrophysics, isotopic geochemistry, and computational astrophysics. Each of these fields is advancing on its own, driven by its own questions and instruments, and the local bubble connects them all, providing a common observational anchor around which their different perspectives converge. This is the nature of great scientific problems. They are not solved by a single instrument or a single discipline. They are illuminated gradually, from many sides at once, by scientists who are each pursuing their own questions, but who occasionally notice that the answers are pointing in the same direction. The three-dimensional picture of the local bubble that emerged from the Harvard-Smithsonian team's work is just such a convergence. A moment when data from stellar astrometry, star formation research, interstellar medium mapping, and galactic dynamics all pointed to the same coherent picture. There will be more such moments. The data being accumulated by current and future instruments is already far more than can be fully analyzed with existing techniques. New computational approaches, including, increasingly, machine learning methods that can find patterns in high-dimensional data that human analysts might miss, are being developed and applied to this problem. The local bubble story has a great deal more to reveal, and the tools to reveal it are being built and sharpened right now. For the moment, though, we can step back and appreciate what has already been achieved. We know that we are inside a vast cavity in the interstellar medium, carved by stellar explosions that occurred before our species existed. We know that this cavity is the birthing ground of new stars. We know that the sun's presence in this cavity may be connected to the history of life on Earth in deep and surprising ways. We know that the bubble is expanding, that it interacts dynamically with its surroundings, and that it is one of many such structures throughout the galaxy, just the one we happen to be closest to, the one we can study in the most detail. And we know that inside this bubble, at this moment, a civilization has emerged that is capable of asking these questions. That is not a small thing. It may, in fact, be the most extraordinary thing of all. Not the bubble itself, vast and ancient as it is, but the fact that inside it, something arose that wanted to know about it. There is one more layer to this story that deserves careful attention, and it involves the heliosphere not as a passive structure inside the bubble, but as an active, dynamic system that shapes the immediate environment of Earth in ways that have become much clearer in recent years. The Voyager probes changed everything we thought we knew about the edge of our solar system. Before those spacecraft made their historic crossings, the boundary between the solar system and interstellar space was largely theoretical. We had models, we had indirect evidence, but we had never actually been there, never taken measurements in situ. When Voyager 1 crossed the heliopause in 2012, and Voyager 2 followed in 2018, we got our first direct sampling of what lies beyond the sun's influence, and the results were both confirming and surprising. Both probes detected a dramatic increase in galactic cosmic ray flux after crossing the heliopause, confirming that the heliosphere does indeed shield the inner solar system from a significant fraction of these high-energy particles. But the two probes did not experience identical conditions, despite being separated by a relatively small angular offset in their trajectories. Voyager 2 detected a thicker and more complex transition region than Voyager 1, suggesting that the heliopause is not a smooth, uniform surface. It has structure, it bulges and indents. Its thickness varies. There are localized features that the two probes sampled differently because they crossed at slightly different points. This structural complexity makes sense physically. The heliopause is the meeting point of two flows, the outward-moving solar wind and the inward-pressing interstellar medium. Both flows are magnetized. Both carry turbulence and instability. The interface between them is not expected to be a clean line. It is expected to be a turbulent, dynamic, multi-layered structure, and the Voyager measurements are confirming exactly that. For the future of our understanding of the local bubble, this matters because the heliosphere is our most accessible tool for sampling the local interstellar medium. The properties of the interstellar medium immediately outside the heliopause, its density, temperature, magnetic field strength and direction, and composition directly influence the heliosphere's shape and dynamics. By studying the heliosphere, we are indirectly studying the bubble. Several future missions have been proposed to extend this kind of in situ measurement further into the interstellar medium. An interstellar probe concept, studied in detail by NASA, would send a spacecraft on a faster trajectory than the Voyagers, reaching hundreds of astronomical units from the Sun in a reasonable mission lifetime. Such a probe could sample the local interstellar medium at multiple points, building up a spatial picture of conditions just outside the heliopause that no amount of remote sensing can provide. In parallel, a generation of new X-ray and ultraviolet observatories is being planned that would provide much higher resolution spectroscopy of the local bubble's hot plasma. These instruments would allow researchers to measure not just the overall properties of the bubble's interior, but the fine-grained structure of its temperature, density, and chemical composition, distinguishing, for example, between plasma that has been recently heated by a shock wave and plasma that has been cooling slowly for millions of years. This kind of detailed spectroscopy would put much tighter constraints on the supernova history of the bubble and on the physical processes governing its evolution. Combine all of this Gaia's astrometry, new X-ray observatories, future interstellar probe measurements, isotopic analyses of geological samples, and increasingly sophisticated computational simulations, and the local bubble is going to come into much sharper focus over the next few decades than it is today. The questions that are currently speculative will become empirically testable. The history of the supernovae that created the bubble will become readable in increasing detail. And the connections between cosmic events and Earth's biological history will either be confirmed and extended or constrained and refined. Either way, our understanding will deepen. Science does not promise that things will turn out to be beautiful or meaningful. It promises honesty, a commitment to following evidence wherever it leads, even when that leads to answers that are complicated or surprising or humbling. What makes the story of the local bubble so compelling is that the honest, evidence-based investigation has produced a picture that happens to be both scientifically profound and, in a very human sense, genuinely moving. We are inside a bubble 1,000 light years across, blown by dying stars, home to newly forming ones, connected through iron and radiation to Earth's deep past, and open through its cleared and quiet interior toward the stars we may one day reach. The universe did not plan this for us, but it built the conditions, star by star and explosion by explosion, and the result is where we are today, curious, capable, and only just beginning to understand. There has never been a better time to be asking these questions, and there has never been a more important time to keep asking them. To bring this story full circle, let us return to the most basic question this discovery invites us to ask. What does it actually feel like, in a scientific sense, to discover that you are inside something? Most discoveries in astronomy are discoveries about things that are far away. We observe distant galaxies. measure the spectra of remote stars, detect gravitational waves from colliding black holes a billion light years off. These discoveries are profound, but they are also safely distant. They reveal the universe beyond our immediate neighborhood. They do not change our sense of where we are. The local bubble is different. It is a discovery about our immediate neighborhood, about the space we actually inhabit, about the conditions that have shaped the 4.6 billion year history of our solar system, and, by extension, the entire history of life on Earth. When you internalize what the local bubble is truly take in the fact that the sun is sitting near the center of a vast, cleared cavity blown by dead stars, your sense of location in the cosmos shifts. Not just your intellectual map of the galaxy, but your intuitive feel for what this place is. We are not in the middle of the Milky Way. We are not on its outskirts. We are in a suburb, in a quiet cul-de-sac of interstellar space, inside a bubble of cleared air in the galactic neighborhood, with the cosmic equivalent of construction zones, star-forming molecular clouds glowing faintly at the edge of our visibility. It is, if you let yourself feel it, a remarkably evocative sense of place. The ancient astronomers who looked up at the night sky had a sense of place too, of course. The Earth was at the center of the universe. The stars were points of light, fixed to crystalline spheres. The cosmos was ordered, beautiful, and human-centered. We outgrew that picture over centuries of careful observation and honest thinking. The Earth turned out to be a planet orbiting a star. That star turned out to be one of hundreds of billions in a galaxy. That galaxy turned out to be one of hundreds of billions of galaxies in an observable universe. Each expansion of perspective was a kind of displacement, a removal from a central, privileged position. But the local bubble offers something that those earlier displacements did not. It restores, in a careful and evidence-based way, a sense that our location in the cosmos is not merely arbitrary. We are in a specific place with specific properties. That place is unusual in measurable physical ways. And those unusual properties appear to be connected, though perhaps not causally decisive to the conditions that allowed us to be here asking about it. That is not the same as saying we are at the center of the universe. We are emphatically not. The universe has no center, or rather every point is equally the center from a certain perspective, and none of them are privileged over any other. But within the Milky Way, within the local swath of galactic space that we can map and study, our solar system happens to be located in one of the more remarkable structures around. A bubble, a cleared space, a harbor. The poetic resonance of this, the sense that the cosmos has somehow prepared a quiet corner for the emergence of curious minds, is not science. It is a human response to scientific findings. But it is not an irrational response. It acknowledges something real, that the conditions of our existence are not simply generic, that they have a specific history, and that understanding that history is one of the most important scientific projects we can undertake. The local bubble will continue to reveal itself in the years ahead. Every new Gaia data release, every new X-ray observation, every new analysis of geological samples and isotopic ratios will add to the picture. The story is not finished. It is, in many ways, just beginning. But what has already been achieved is remarkable. We know the bubble is real. We know its size and shape and approximate age. We know how it was formed and what it is doing to the gas around it. We know that it has influenced the history of star formation in our galactic neighborhood and, potentially, the history of life on our planet. We know that it is one of many such structures, and that mapping those structures will illuminate the large-scale dynamics of our galaxy. We are inside a 1,000 light-year bubble, floating near its center, looking outward through its cleared space at a universe that is rich with structure, process, and history. And we are, improbably but undeniably, aware of all of it. That awareness is the most astonishing thing the bubble contains. Let us pause for a moment and think about what it would take observationally, technologically, and intellectually to even imagine that you might be inside a bubble 1,000 light years across. This is not like looking at a tide pool and observing that you are standing on a rocky shore. The scale is so vast, and the medium so thin and invisible, that detecting the bubble at all is an extraordinary achievement of human ingenuity. Think about the challenge. You cannot simply look around and see the bubble's walls. 1,000 light years is so enormous that the nearest portions of the bubble's surface, the star-forming clouds in Ophiuchus and Taurus, appear to us as isolated, independent objects scattered across different parts of the sky. They look unrelated. They did not announce themselves as being connected pieces of a single coherent structure. The connection had to be inferred from careful measurement, precise three-dimensional positioning, and a willingness to ask whether seemingly separate things might actually be parts of a larger whole. This is one of the defining challenges of science in general, and astronomy in particular. Recognizing structure in systems too large, too slow, or too indirect to be seen in their entirety. A geologist studying rock layers in a canyon is reading the history of a planet. An archaeologist piecing together pottery shards is reconstructing a civilization. An astronomer mapping star-forming regions across the sky is, it turns out, reading the expansion history of a superbubble that encloses us. In each case, the structure becomes visible only when you have enough pieces and when you have learned to ask the right questions. The local bubble became visible when the combination of Gaia's stellar positions, decades of interstellar medium observations, and sophisticated computational tools gave researchers the pieces they needed. And when Alyssa Goodman, João Alves, and their collaborators thought to ask whether all of those young star clusters and molecular clouds might be telling the same story. That act of synthesis, of bringing together disparate data streams and recognizing the coherence hidden within them, is science at its most creative. And it is a reminder that some of the greatest discoveries are not about finding something completely new, but about finding the pattern connecting things we already knew. The molecular clouds of Ophiuchus, Taurus, and Perseus were known. The Scorpius-Centaurus association was known. The diffuse X-ray background was known. The anomalously low density of the local interstellar medium was known. What was not known, not clearly, not in 3 dimensions, was that all of these things were manifestations of the same underlying structure: the bubble's formation, expansion, and current state. The moment of seeing that coherence for the first time must have been extraordinary. Scientists are trained to be cautious, to check their results, to look for alternative explanations. But there are moments in science when the data arrange themselves in a way that speaks unmistakably, when the pattern is clear and the interpretation compels. The local bubble map appears to be one of those moments. The reaction from the broader scientific community, the enthusiastic reception, the rapid follow-up work suggests that other researchers see the same clarity. Moments like this are rare. They are also cumulative. Each discovery that reveals a new layer of cosmic structure makes the next discovery slightly easier, because it adds to the conceptual framework within which new observations can be interpreted. The local bubble adds something important to that framework: the recognition that our position in the galaxy is not a passive, inert circumstance, but an active, physically meaningful one, connected through cause and effect to events that shaped both the stars around us and the conditions of our own existence. That recognition does not resolve every question. Far from it. It opens dozens of new ones. But it does something that good science always does. It changes the questions worth asking. Before the local bubble was mapped in 3 dimensions, the questions were mostly about properties of individual objects: this star, that cloud, this X-ray feature. After the mapping, the questions became about relationships. How did this cloud form from the bubble's compression? How did those supernovae set this chain of events in motion? How does our own solar system's history connect to the bubble's history? Questions about relationships are, in many ways, deeper than questions about individual objects. They get at the structure of the cosmos, at the web of causes and effects that connects things across space and time. And the local bubble has given us one of the most clearly drawn pieces of that web within our reach. There is a practical dimension to this as well. As space agencies and private organizations begin to think more seriously about long-term human presence beyond Earth, the large-scale structure of the interstellar medium around us is going to matter. Near-future space exploration is limited to the inner solar system, but on longer timescales, generations from now, the question of interstellar travel will become less fantastical and more engineering-focused. And at that point, knowing the density and structure of the medium that a spacecraft would travel through becomes a practical engineering input. The local bubble's low-density interior reduces one major risk collisions with dust and gas: The star-forming regions on its surface, though too far to reach in any near-term scenario, could become eventual destinations if the technology catches up to the aspiration. The mapping of the bubble's structure is, in this sense, early reconnaissance for an exploration that may happen tens of thousands of years from now. We cannot know what humanity will accomplish on those timescales, but we can know that the maps we make today will still be accurate then. The bubble is 14 million years old. It will persist for millions more. Whatever species or civilization occupies our solar system in the distant future will still be inside this structure, still surrounded by these forming stars, still positioned as we are now near the center of a vast cleared space in the Milky Way. The knowledge we are building now is not perishable. It is a permanent part of what has been learned about the universe. That permanence is one of the most quietly satisfying aspects of scientific discovery. The observations are made. The data are preserved. The papers are written and peer-reviewed and published. And even if every person who made the discovery is long gone, the discovery itself remains a fixed point of knowledge that subsequent generations can build on. The local bubble, mapped and understood, is now a permanent part of humanity's knowledge of the cosmos. It joins the heliocentric model, the theory of stellar evolution, the Big Bang, the existence of exoplanets, and countless other discoveries as a pillar of our scientific understanding of where we are and how we came to be here. It is a contribution that will not be undone. The bubble exists. We are inside it. We know how it formed, and that knowledge is ours to keep. When you step back and look at the full arc of this discovery, from the first puzzling X-ray detections in the 1970s to the full three-dimensional mapping of the bubble and its star-forming walls published, in the 2020s, what you see is a 50-year process of science working exactly as it should. Puzzling data came in. It was preserved, shared, and built upon. New instruments were developed that could address the questions raised by earlier observations. Theoretical models evolved to keep pace with new data. And eventually, a generation of researchers with the right combination of instruments, data, and computational tools put the picture together. That is how transformative science happens. Not with a single eureka moment, but with the slow accumulation of evidence and the gradual crystallization of insight. The local bubble was always there, surrounding us. We have been inside it for 5 million years. But we only recently developed the eyes to see it and the minds to understand what we were seeing. That understanding continues to deepen. And the bubble, ancient and enormous, quietly goes on expanding. Final character count confirmation.